In this module, we'll be learning about correlation. In Case 1, we've learned about several statistics to summarize students' FCAT scores and to index the shape of the FCAT distribution. That is, we paid attention to only one variable, FCAT scores. In addition to FCAT scores, now we add one more variable, student attitude toward school, in our research scenario. And we're interested in exploring the relationship between FCAT scores and students' attitudes toward school. In addition to knowing how students perform on the FCAT test, the teachers of East Westside Elementary School are interested also in whether students' performance is related to their attitude toward school. Therefore, the teachers not only collect students' FCAT scores, but also measure of students' attitude toward school with a 20-item instrument using a 5-point Likert scale. For instance, strongly disagree to strongly agree. The maximum attitude score is 100 and the minimum is 20, with higher scores suggesting more positive attitudes. Presented here are the data for the 50 students from East Westside Elementary. The variables included are gender and scores from the FCAT and attitude survey. Our analysis plan includes creating a picture of the relationship between two quantitative variables. This picture is called a scatter plot. In addition, we'll calculate a single number summary of the relationship called a correlation coefficient. In order to calculate the correlation coefficient, we will calculate two other statistics related to relationships, the sum of cross products, SCP, and the covariance. A scatter plot is a type of graph that can be used to explore or illustrate the nature of a relationship between two quantitative variables. A scatter plot has two axes, x and y. Any observation contributes a point, xy, to the plot, indicating their scores on variable x and variable y. Commonly, the variable on the x-axis, that is horizontal axis, is thought of as the independent variable, or predictor, and the variable on the y-axis, that is the vertical axis, is the dependent variable, also known as an outcome or criterion variable. By plotting these points for a whole sample, scatter plots help you visualize patterns in the data and guide you in deciding what statistics are most appropriate for analyzing your data. Typically, all observations are used to create a scatter plot. To simplify our demonstration of the scatter plot, we extract the FCAT scores and attitude scores of 6 students from the sample of 50 students. This is what the scatter plot for the 6 observations looks like. The horizontal axis represents the attitude scores x, and the vertical axis represents the FCAT scores y. A dot in the scatter plot represents the attitude score and the FCAT score xy for one student. Because we have 6 students in this demonstration, we have 6 dots in our scatter plot. Each student contributes 1 point to the scatter plot. For instance, student 1 has an attitude score of 45 and an FCAT score of 270. You can find the score of 45 on the x-axis and the score of 270 on the y-axis. The crossed point in the graph is a dot to represent student 1, 45, 270. Based on the scatter plot you draw, you can ask yourself the following questions regarding your data. Is there an apparent pattern in the data? Is it a linear trend? A curvilinear relationship? What does the spread of the data look like? Do you have an even distribution of points along the range of scores, or do you have clusters? Are there outliers or cases that do not seem to fit the pattern? This scatter plot represents the data for Case 2. Can you describe the data based on the scatter plot? Hint: try answering the questions on the previous slide. In this scatter plot, the relationship is linear. There is an obvious cluster, and there are 2 outliers. Let's look at how the correlation coefficient is calculated. In addition to the graphic illustration, a statistic called a correlation coefficient is commonly used to represent a relationship between 2 quantitative variables. 2 variables measured on the same set of participants may or may not be related to each other. For example, there is no plausible reason why shoe size and the number of miles one drives to work would be related. However, shoe size and height may be related because knowing information about a person's height would help you predict his or her shoe size. To obtain a correlation coefficient, we will work through the 3 statistics listed in the analysis plan: sum of cross products, SCP, covariance, and correlation coefficient. Recall the processes of calculating the standard deviation, including deviations from the mean, the sum of squares, the variance, and the standard deviation. For the correlation coefficient, we will need to compute the standard deviation for FCAT scores and attitude scores. In addition, a 3-step process is required for computing the covariance. The steps are as follows. Find the deviation of each score from the mean for both the FCAT score and the attitude score. Compute the sum of cross products, denoted SCP. Compute the covariance, denoted S sub x sub y. Step 1 is to calculate deviation scores for FCAT scores and attitude scores. Recall that the deviation score is the observed score minus the mean, and the mean is the average score for the 6 students in our demonstration data. Take a moment to review the mean calculations for student attitude scores and the FCAT scores. In the scatter plot, we can draw 2 lines to represent the means for both score data. Click on the Show Scatter Plot to see the scatter plot. This slide shows the data points for the 6 students along with the means of the 2 variables, which are shown as lines. The mean of the 6 FCAT scores is 300, and the mean of the 6 attitude scores is 57.5. Then each observed score for attitude is subtracted from the mean attitude score, that is x minus x bar. And each observed FCAT score is subtracted from the mean FCAT score, that is y minus y bar. In the scatter plot, this process represents obtaining the distance from the point to the mean line. Click on the Show Scatter Plot to see the scatter plot. This slide shows the scores for student 5, but the point on the scatter plot has been replaced with distances from the means for both variables. For example, the value of negative 27.5 for the attitude variable x means that student 5's attitude score was 27.5 points below the mean of the 6 students' score. Step 2 is to calculate the sum of cross products. The process is to multiply the attitude deviation score with the FCAT deviation score for the same person. That is x minus x bar times y minus y bar. This is called a cross product. We can compute a cross product for each person. This graph shows how the cross product is calculated for student number 5. The attitude deviation score, which is negative 27.5, is multiplied by the FCAT deviation score, which is negative 130. The product of these 2 deviation scores, which is 3,575, is the cross product for student number 5. Mathematically, we provide an equation for the sum of cross products, SCP, which uses the summation symbol sigma to indicate all the cross products being summed, starting with the first score and ending with the nth or last score. The sum of cross products is not easy to interpret, so there are more steps needed in getting to the correlation coefficient. For our small demonstration sample, the sum of cross products will be as follows, each parentheses representing the cross product for students 1 through 6 in order. Thus, the sum of the cross products for the 6 students is 8,000. We present a formula for covariance indicating the sum of cross products is divided by n-1. The symbol S subscript xy is used to represent the covariance between variable x and variable y. Note again that we divided by n-1 instead of n in order to obtain the unbiased estimate, or in other words, this creates a fancy average cross product. The covariance for our small demonstration sample will be as follows for SCP equals 8,000, n equals 6. To find the covariance, we start with 8,000 and divide by 6 minus 1, which is equal to 1,600. However, the covariance is somewhat difficult to interpret because the size of the covariance depends on the units in which the variables were measured, like raw scores. We must standardize the covariance so we can compare the strength of relationships across different variables or studies. The Pearson product moment correlation coefficient, also referred to as the Pearson correlation coefficient, is the standardized covariance. The Pearson correlation coefficient is calculated by dividing the covariance by the product of the standard deviations for the 2 variables of interest. Formulas for the Pearson correlation coefficient and the 2 standard deviations are presented here. The symbol R subscript xy is used to represent the Pearson correlation coefficient between variable x and variable y. S subscript x and S subscript y represent the standard deviations for variables x and y, respectively. Finally, here's the Pearson product moment correlation coefficient for our small demonstration sample. The covariance is divided by the product of the standard deviation for attitude scores and the standard deviation for FCAT scores. The variance is 1,600. The standard deviations for X, attitude scores, and Y, FCAT scores, are 19.17 and 88.09, respectively. The correlation coefficient is 0.95, which is extremely high. The next 2 slides review the calculation of these standard deviations. This slide shows the calculations of the standard deviation of the attitude scores for the 6 students. The sample mean attitude score, shown at the bottom of the second column in the table, is subtracted from each observed attitude score, shown in the second column. To create deviation scores, see the third column in the table. Each deviation score is squared, and these squared deviation scores are added together to obtain the sum of squares. See the fourth column. The sum of squares is divided by n-1 to obtain the variance. Finally, the square root of the variance is the standard deviation. See the formula shown on the slide. This slide shows the calculations of the standard deviation of the FCAT scores for the 6 students. The same process is followed. Calculate deviation scores, square the deviation scores, add them together to get the sum of squares, divide by n-1 to get the variance, and take the square root to obtain the standard deviation. Now let's apply these same procedures to our data in case 2. Recall that the Pearson correlation coefficient is calculated by dividing the covariance by the product of the standard deviations for 2 variables. Therefore, we first calculate standard deviations for the FCAT and attitude scores. Then calculate the covariance between FCAT scores and attitude scores. Finally, compute the Pearson product moment correlation coefficient based on these 3 values. This shows the computational processes of standard deviation for attitude scores, which is 16.01. This shows the computational processes of standard deviation for FCAT, which is 62.91. This shows the sum of the cross products between the FCAT and attitude scores, which is 35,275. The covariance for our sample will be as follows. The sum of cross products, 35,275, is divided by n-1, which is 49, to obtain the covariance of 719.90. The correlation coefficient, R subscript xy, is the covariance between x and y, divided by standard deviation of x times standard deviation of y, which is 0.72. We can say that the Pearson correlation coefficient between students' FCAT scores and attitude scores is 0.72. The question is what the coefficient of 0.72 represents. To answer this question, we're going to explore interpretations of a correlation coefficient in terms of the direction and strength of the relationship.